Okay, so what we want to do is look at the different interpretations of the integral, and so we already have one that we've been using quite a bit, and that is that if you have a function that represents the velocity, then the area underneath the curve is going to represent the distance traveled. Now, we're going to elaborate a little bit more on that. Let me draw another picture that has, so let's say we're looking at the same velocity deal. And so let's say we're starting at this point A, and let's say this is B. Now, so if this represents velocity, and then down here, of course, that would be time. So let's call this velocity little f of t. Okay. Now, if you find the integral from a to b of f of t dt, so notice that you find the area underneath the curve. This one up here is positive, and this one down here is negative. So this is really, it's not really the distance traveled. It's more so the displacement. So basically, it counts this. The positive is when you're moving forward, and then this negative area represents you moving backwards. So this is kind of like you take 3 steps forward, 1 step back, and then you go half step forward, and so on. So the displacement, remember, is basically the distance from your starting point. Now, if you want to find the total distance that you traveled, then you would have to count the negative area as positive as well. So that just needs a small modification. You just get the integral of the absolute value of f of t dt. And so this is going to be the distance, the total distance traveled. And we'll do an example in a little bit. Okay, now that's for velocity, and but let's say this works. The interpretation works for any kind of rate. For example, if let's say we have a function right here, and this is the rate of a population change, rate of the population growth on Shelter Island, let's say. Some random island. Let's call it R of t. And let's give it some units. The units are really important. Let's say it's in number of frogs per year. Okay, so those are the units of this function, which gives you the rate of change of the population of frogs on Shelter Island. Okay, now if you find the area underneath the curve, let's not do A and B. That's a little bit too abstract. Let's do, oh look, checkerboards. Let's do from 2 to 7. Okay, so since this is in frogs per year, then this the horizontal axis would have to represent years, and so this is frogs per year. Okay, so if you find the area underneath the curve, what this basically tells you is that this is going to tell you the amount of frogs, gained from year 2 to 7. So this is basically counting the amount of whatever this rate explains. So in this case, it's frogs, but this can be really anything. I mean, if, for example, this represented the rate of child growth, then the area underneath the curve would represent the amount of growth that the child had. If this represented the, I don't know, how fast water flows down a tube, then the area underneath the curve would represent the amount of water that would flow through the tube in this time period. Okay? All right, so hopefully that makes sense. Now, let's do an example. Let's say you have a particle. Let's see. Let's not make it a particle. Let's say it's a car. And this car has a velocity function of, let's make it something simple just to start off. So let's say we have this car and its velocity is explained by the function 4t plus 5 from 0 to 5. And let's say that this is in miles per hour. Okay, now let's interpret. Let's say we want to interpret and find the following: the integral from 0 to 5 of 4t plus 5 dt. Okay. So this integral, basically what you're doing is you're getting the integral from 0 to 5 of the velocity of this car. So now, to be able to interpret it, it's really, really important that you have the units. So the interpretation of this is basically when you find the integral from 0 to 5, this is going to give you the amount of miles traveled from 0 to 5 hours. So when you find the integral, the units are in miles, and these from 0 to 5, these are hours. So this is going to give you the displacement, or how far your car is, from your starting point, from 0 to 5 hours. So the first 5 hours that you drive, how far did you go? Okay, so let's actually find it. So here we have, we just use the fundamental theorem of calculus. 4t squared over 2 plus 5t from 0 to 5. And so then I have, plug in 5. I get 5 squared is 25 times, 4 and 2. Let's just change that to 2. So 25 times 2, that's 50 plus 25. And then plug in 0, that's going to be just minus 0. So this is 75, and then 75 miles. It's really important, the units in this case. So this just means that the car in the 5 hours, it drove 75 miles. Okay, so let's do another example. Let's say we know the acceleration of a particle. I don't know, a car, a bee, turtle, whatever you want, whatever you feel like, is t plus 4. And let's say that we know that the velocity at time equals 0 is equal to 5. And so let's say we want to find. So let's say we want to find the distance traveled. The distance traveled from 0 to 10 minutes. Now I haven't given it units, but let's say the units for the acceleration are feet per minute squared. Okay. All right, now to find the distance traveled, notice that you have the acceleration here, and you can't find the distance traveled just with the acceleration. But we can do, something similar to what we did when we first learned antiderivatives, is that if we have the acceleration function, we can find the velocity function. So the velocity function is the antiderivative of the acceleration, which would be t squared over 2 plus 4t plus c. And so then remember, you have your initial conditions. You have that when t is equal to 0, v is equal to 5. So you just plug those in. And when you do that, you're going to get that c is equal to 5. So this means that the velocity function is t squared over 2 plus 4t plus 5. Now at this point, you have two options. You can either find they're actually kind of similar. You can either find the position function. The same thing that we did when we first learned antiderivatives. Find the position function, and find the distance traveled using that, or using integrals. Now, since we're in the integration chapter, let's do using integrals. So the distance traveled, remember, is the integral from 0 to 10 minutes. So it's going to be from 0 to 10. And then it's going to be of the absolute value of t squared over 2 plus 4t plus 5. Okay, now, and then dt, don't forget. But notice that this function is always positive, so I don't need the absolute value. So I can just erase that. Oh, the checkerboard again. Maybe I should put some white background over there so you don't have to look at the checkerboard. But oh well, it's too bad. Maybe I'll just put a parentheses there instead. Okay. Hopefully I don't have to erase again. Oh, look at that. Magic. They disappeared. Okay. Anyways, so then we use the fundamental theorem of calculus here. So find the antiderivative. So that's going to be t cubed over 6 plus 2t squared, because you add 1, divide by 2. So that's going to turn into 2. And then plus 5t. Now notice there's no plus c here because it's a definite integral. And so I'm just going from 0 to 10. Okay, so then I'll plug in 10. 10 cubed is 1,000 over 6 plus 10 squared is 100 times 2 is 200 plus 50. And so what I get is 1,250 over 3, or about 416.67. And what are the units? What are the units? Oh, I need the units. The units are feet. So that's how far our car slash frog slash turtle, whatever you chose, traveled. And that's it. Nice work.